Okay, so indeed my name is Modarnos, and let me tell you a little bit about my research in a sentence. My research spanned on a wide range of topics, covering structure formation in the early universe up to the dynamics of planets and stars. And there is one thing that connects them all, which is physics, and specifically gravity at different scales. And this is what I think astrophysics is all about. We're solving physics problems in astrophysical settings. And this is what I'll show you today. I chose one setting because this is a second workshop, so this is planetary settings. And I'm going to explore different dynamical processes. So when we say dynamical, it's pretty much gravitational interactions between different orbits. So dynamical processes that affect orbits in a planetary system. And this is dated back all the way to Kepler and Poincaré, who laid out the foundations of pretty much everything I'm going to talk about today. And however, in contrast to these very old theories, there were a lot of new excitements, observations, such as the one from Kepler, that completely transformed how we view planetary systems today, what we think that planetary systems should look like. And we have a wealth of discoveries. I'm kind of a little bit rushing through this because I assume that some of these, at least this, you've seen before. So we have a wealth of discoveries, and we can now do some statistics. And we found many, many puzzles and many mysteries that challenged old notions and promoted new ideas. And it seemed to emphasize that dynamical interactions after the planets have formed play a very, very important role. Now, of course, depending who you'll talk with, people will tell you different things. But since this is my talk, I will emphasize dynamics. Now, of course, if I want to understand what people thought, we need to look at our solar system. So our solar system is very ordered, very neat. All the inner planets are small, they're rocky. All the outer planets are gas giants. They're where we thought they should be formed. Everything is relatively circular, more or less. They're all orbiting in the same direction as our star spins. And most of them they're mostly coplanar, up to about 7 degrees. But 7 degrees is almost nothing compared to what I'm going to show you in a minute. So this system is really ordered, and we understand this with the vanilla story of formation. The formation that we already know, it's not complete, but this is where everything originated. So we have a gas cloud that contracts due to its own gravity. As it contracts, it conserves angular momentum, which means that I have lots of mass in the center and lots of angular momentum in the outskirts. So I have one angular momentum I'm forming that determines the star in the middle and a disk. And if I'm forming planets in the disk, then I should expect that all the planets will be coplanar mostly. All of them should orbit in the same direction as the star spins, again, because I have one angular momentum in the system. And it should work very well. And it worked very well for our own solar system, because the era of thinking, at least, came from this side to this side and not the opposite. But let's look at outer solar systems. So when we look at outer solar systems, the first thing we notice is that there are some gas giants extremely close to the host star. Very close, I mean one-day orbit. So we need somehow to force them far away where there are still maybe ices and bring them all the way in. And we also notice that many of them are misaligned with respect to the stellar spin axis. So a system like this I would call aligned, because the planet is orbiting in the same direction as the star spins. But many of them are misaligned, basically tilted, and some are even retrograde, orbiting in the opposite direction. And this is a puzzle. How can we do that? We observed other puzzles. For example, we found many, many, many super-Earths very, very close, closer and inwards to Mercury's orbit, which is a surprise by itself, again, because inwards to Mercury we have nothing, at least in our own solar system, and we're the most important, right? This is why we're doing all of this. And we also observed some unordered systems where there is a slightly giant, bigger planet inwards to a smaller planet. And sometimes we also find misalignment. So I was lazy with having yet another animation here. Basically, and of course, we have many eccentric planets, which is also surprising because our solar system doesn't have any eccentric planets, or at least major eccentricities. The mere diversity of orbits inwards to Mercury, in this movie I'm sure you've seen many times by Alex Parker, is really, really impressive. And it's in complete contrast to this vanilla story that we liked with having a disk here. And it emphasized the need for astrodynamics. So basically I'm saying from these old times, it's still alive. And thank you for laughing. From here and there, I'll have some jokes. Feel free not to laugh. I'm not a very good joker. No, the pressure. Okay. Yes. Yes. So I'm sorry. I'm doing lots of problems, I guess. Oh man, what did I do? Not a very good multitasker. All right, so what I want to do today, I'm going to give you tastes of dynamical processes. And it's taste because I can spend an hour on each of these processes. And if you know me, you know that I'm completely obsessed with this last one. So this, it will be a little bit more than a taste, or at least depending how long I'll have. And I also want to talk about resonances, because many of these happen because resonances. So I'm going to show you how we can understand a lot of this just if we remember the pendulum, the simple pendulum. Okay, but I want to start with what is called planet-planet scattering. All right, so it's exactly like it sounds. We're scattering planets, like in this movie, just like billiard balls. Of course, they do not touch each other. This is gravitationally scattering. And many times, what happens from this idea is if you start the planets rather compact, they start to interact with each other, become a little bit unstable. One of the planets ejects, like in this cartoon, in this movie, and we are left with an eccentric planet, a faraway planet, a more stable configuration. Usually we get somewhat high inclinations and eccentric planets. This is one example. As a function of time, we see here 3 planets, 1, 2, it's hard to see, and 3. And here we have that the second planet got ejected here. And then we can ask, what happened here? Here we have high eccentricity. The eccentricity develops. So basically, the planet comes very, very close to the star. We can, and tides will start to work. And we'll shrink the orbit and circularize it. So we can add some sort of recipe for tides. And we will talk more about the recipes for tides later, hopefully. And we can get, that was the ejection. And then we can get, here they got a hot Jupiter after the tides. So we have circular behavior, and they got circularized and shrink the orbit. And this is planet-planet scattering. Another interesting thing that we observe many times in planetary architectures are mean-motion resonances. And again, for this, to do justice to this field, I need at least an hour, so I'll try to do it in 2 minutes, and we'll see how we'll do. What are mean-motion resonances? Basically, resonances is when you have at least 2 natural frequencies in your system, and they're matching one another up to some number. So here, for example, if I'll have the periods of 2 orbits close to one another up to this fraction where n and m are integers. And they should be small also, so it will be more profound. If n and m are very large numbers, even if they're integers, probably their effect is small. And we see it a lot in our own solar system, for example. This is a very famous, doesn't work, a very famous something that doesn't work. So it's supposed to be a movie. I don't know why it doesn't work. Oh, it does work. That's good. Okay, so we have here a movie of the Galileans moons. Okay, thank you. Galilean moons that are in resonance. This is called the Laplace resonance. It's 1 to 2 to 4 resonance. And we also have this in an exoplanet system, for example. So basically, we get that, that the periods between them are in 1 to 2 to 4 resonances. So these are the ratios. Now, resonances can lead to stable configuration, like this one. But sometimes it can lead to unstable configuration, like this one. So we know that these are mean motion resonances with Jupiter. This is our asteroid belt, that we have these places where are depleted from asteroids simply because these became extremely unstable and ejected away. We also see this in Saturn's ring from mean motion resonances with Titan. So resonances could either lead to stabilization of the system that otherwise would not be considered stabilized sometimes, and unstable systems. So it's interesting to look at this. If we look at extrasolar systems, we expected the following. We expected that we will have some resonant trapping basically because of migration rates. But reality showed us differently. So here we see the number of planets as a function of the outer planet over the inner planet. This is also planet candidates. And you can see here that there is not, yeah, I know that you probably cannot hear me very well. I'm sorry, I don't know what to do with this. And you can see here that there is, where you would expect the mean motion resonances to do something, they don't do much. Maybe here, there is some deficit here. They usually, we find some, and there's some enhancement here to the 3 to 2 resonance. And that was a very interesting puzzle. What is going on? And whenever there is a puzzle in science, there are many, 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 many answers. And I cannot do justice to all the answers of what is going on with the mean motion resonances for exosolar systems. So all I did is just listed here some explanations that may explain, and that may give some hints on what is going on, and probably there is a combination between all these explanations, and there are more explanations. Okay. Oops. Nope. All right. So, what I call classical secular evolution. Now, let's think about our own solar system again. This is again Poincare times. And let's have, just for simplicity, 2 planets. And they are rather circular and rather coplanar, exactly like our own solar system. On orbital timescales, nothing interesting has happened. The planets are just orbiting around. The system is rather stable. And that means that I can basically average over the orbit. Averaging over the orbit means that I can smash the mass around and treat the orbits as 2 wires interacting with each other. And now if I have 2 wires interacting with each other, this is called the secular approximation. So whenever someone tells you, I'm applying the secular approximation on such and such orbit, on such and such system, that means that they averaged over the orbit and looked at long time scales. What does it mean to average over the orbit? It means that, well, I actually don't have a lot of time to ask you guys questions as I wanted. It means that the energy is conserved here and here. If the energy is conserved, that means that the semi-major axis of the system is conserved as well. So if I have 2 conserved, hi, sorry. Anyway, 2 conserved energies. You distracted me. 2 conserved energies. Yeah, I lost my train of thought. Where was I? Secular. So if I have, let's go back. I'm smashing over the orbits, and I have 2 wires interacting with each other. The energies are conserved. Semi-major axis is conserved. Everything that happens because I have angular momentum exchange between the 2 orbits. I can this classical approach is valid as long as my eccentricity is small, up to 0.3, and my inclination is small, again up to 0.3 radians. So I can have it a little bit inclined. But we can take everything into a computer. So apart from having very interesting new times of new exciting times of new observations, we also live in a time where computers are better. So we can solve, for example, Poincaré's problem of just thinking about the stability of the solar system. And this had been done first. So here is Poincaré thinking about the stability of the solar system. Has been done, for example, to show, so solving the entire system, not constrain ourselves now to 0.3 eccentricity and 0.3 inclination, so solving the Hamiltonian. Here we see the maximum eccentricity of Mercury, and this is as a function of time in million years. And these are different realizations of our solar system, and you can see that Mercury every now and then can be ejected. So this is a nice way to see how even a very old theory is now, we can now address long-standing questions like the stability of our solar system. All right, so we reviewed very quickly different dynamical effects. We can now go to what I like to call the eccentric quasi-Lidov mechanism. So if we're thinking about the classical, the very classical secular problem where everything is rather circular and almost coplanar, now we can use, we can relax those assumptions. We can have it eccentric, we can have it very inclined, but we have to pay a price. And the price is that for stability reasons, we have to constrain ourselves at least to some small number, and it has to be hierarchical. So what we'll do, we'll just put a perturber very far away. So this perturber very far away can be whatever inclined or eccentric, and this guy can be inclined and eccentric as well. And the advantage of doing this way is that it will give us some intuition of what happened if we will add and relax these assumptions that we have here of hierarchical and small number like 3. Okay, and this was studied way before us, not as far as Poincaré's times. This is the 60s. Happy times were the 60s. And before I'll explain what happened, I want to do some definitions. So here I have 3 body, 1, 2, 3. I'm going to put this in a very tight orbit and this guy in a very far away orbit. So this way I have a stable configuration. And again, I'm going to smash the mass around. So imagine Super Mario again smashing the mass around and creating 2 wires interacting with each other. And my definitions will be as follows. First, I can define the angular momentum of the inner orbit, and then I'll define the angular momentum of the outer orbit. So inner for me is 1, and outer for me will be 2. I will also add this. We will do this very complicated adding of the vectors again later. And I can define the total angular momentum. And I will put my z-axis along the total angular momentum. Why should I put the z-axis along the total angular momentum? What is so special about the total angular momentum? It's conserved. Excellent. It's conserved. And it's conserved because there is nothing that will destroy the conservation of total angular momentum in this system. Good. I can also define the inclination that will be the angle between L1 and L2. All right, as I said, this had been done before us. Let me describe what Kozai did. He took the 3-body Hamiltonian, expanded in semi-major axis ratio, because the ratio of the inner wire to the outer wire should be a small parameter if I put this guy far enough. And sorry. And after he expanded in semi-major axis ratio, he averaged over the orbit. So he smashed the mass around and reduced the problem from 3-body to 2 wires interacting with each other. And then after he did this, he truncated the Hamiltonian up to the quadruple level of approximation, which is the lowest level of approximation. The quadruple is the semi-major axis ratio to the power of 2, and it's called quadruple. And this is what he saw. He saw that the eccentricity, that if he started with an initially inclined system, that the eccentricity of the inner orbit and its inclination oscillates. Where it's less inclined, it's more eccentric. And when it's more inclined, it's less eccentric, like this, basically, and going back. And he also found this conservation law that is very famous to be quasi-conservation law, or quasi-integral of motion, which is the z component of the angular momentum. Remember, our z-axis is along the total angular momentum, so this is the projection. And it's 1 minus e squared times cosine I, and it's equal to constant. And here we see these oscillations. Less inclined, more eccentric. More inclined, less eccentric, and vice versa. It also means that if I start below 90 degrees, I can never go above 90 degrees. Why is that? Very, very easy question. I cannot change the sign of the cosine. So I know that everyone knew that and were embarrassed to answer. So the question that I want to ask now is this conservation law is really constant. And here again are my two wires. So I'm going to have a slight technical part in my talk, but it's not going to be very complicated. We're going to add the vectors, we're going to see the vectors, we're going to remind ourselves what the Hamiltonian is, and we'll see that actually it's not constant. So I gave away the punchline. But here is the inner orbit and here is the outer orbit. And we're going to add the vectors. So I'm going to add the outer and the inner together. I can write angular momenta as this, 1 minus eccentricity squared. Because if I have something which is almost on a radial orbit, it has very little angular momentum in it. And adding the two vectors, I get the total angular momentum. And here is the equation, L1 plus L2 equal to L tot. Very simple equation. Then, remember that the L tot is along the z-axis. I can define now two angles. I1, which is the angle between the inner orbit and the total angular momentum, and I2, which is the angle between the outer orbit and the total angular momentum. So I can define now z, the z component, just by looking at the projection. So the L1 just gets a cosine I1. So square root of 1 minus E1 squared cosine I1. And also, L2 gets the same thing. L2 sub z gets square root. This is the angular momentum of the outer orbit, cosine I2. OK, we have everything we need now to continue with our complicated equation over there. So here it is. Let's rearrange this. So I just moved the L2, the outer orbit, to here. L2 equal to L tot minus L1. I'm going to take the square of this. Here is the square. L2 square equals to L tot square plus L1 square equal to minus 2 L tot L1 cosine I1. We can recognize this as the z component of the inner angular momentum. What? Because I said it is constant. Talking about Kozai, here he is. This is a fairly recent picture of him taken by David Polishuk. And should be credit, but I don't see it. And in his paper that he wrote in 62, so thinking about science, the first person to talk about the Kozai was Lidov. This is why I call it the eccentric Kozai, Lidov, because I want to recognize Lidov's work. He presented his work at a conference, Kozai sat at a conference and wrote a paper in English, because Lidov wrote his paper in Russian, which took a lot of time until it was translated into English. So just an interesting anecdote in science, how things work. So it's known for a long time as the Kozai mechanism, but Lidov came first. Anyway, in his paper, this is what Kozai found. To the lowest order of approximation, which is called the quadrupole, he found that the angular momentum of the outer orbit is constant. What does it mean? It means that that there is a symmetry for rotation for the outer orbit. The inner orbit doesn't know if the outer orbit is this way and this way. So what does it mean? When can I use the quadrupole level of approximation? If there is a symmetry for rotation, I can only use it if the outer orbit is circular. OK, fine. So we will, if I want to use now the quadruple level of approximation, this a1 over a2 to the square, then I need to work in a circular orbit. The outer orbit will be circular. Fine, let's do that. And then he also found that the z components of the angular momentum of the inner orbit and the outer orbit, here it is, are conserved as well. These are the famous Kozai constant of motions. And basically, he only found that the angular momentum is the only thing that changes with time. This is the only thing, the angular momentum of the inner orbit. And where does it come from? Let me remind you a little bit of Hamiltonian mechanics. In Hamiltonian formalism, every angle or every momentum has its conjugate coordinate. So every angular momentum here has its conjugate angle. And to know if an angular momentum is conserved or not, I need to look for at the Hamiltonian and to see if I see the coordinate there. This is because P dot is dHdq, where P is the momentum and Q is the coordinate. So we only saw that the Hamiltonian depends on the conjugate coordinate of the angular momentum. This is called in the field the argument of periapse. This is an angle in the plane of the ellipse. So if I'm forming this ellipse, it's the planes that tell me where the ellipse points at. And that's it. So this is this angle. All right, we have everything we need. Let's go back and look at this equation. These two are conserved. The total angular momentum is conserved by definition. L2 is conserved. We said that this is what he found to the lowest order of approximation. Approximation is fine as we do this. These are spherically symmetric behaviors. If I work in a circular orbit, everything should work, so it's okay. We also get that the z component is conserved. Do you see the problem here? I have things that are red that are constant equal to something that is changing with time. And all I did is adding the vectors. So there is a fundamental problem here in this entire formalism. The problem came up to be that they were missing these two angles. These angles, they're called the longitude of ascending nodes of the inner and outer orbit. I hope you see that there is some color coding. This goes with this. So red omega 2 goes with the z component of the angular momentum. So this longitude of ascending nodes, this is a 3D angle, goes outside of the plane of the ellipse that tells me something about the 3D tilt. This is why it has something to do, it's conjugate momentum, it's the z component of the angular momentum. So it's outside the plane of the ellipse. And the reason that they miss this is because these two have a very specific relation if I have total angular momentum conservation in the system. They're equal to pi. But that is fine. The fact that they are equal to pi doesn't mean that I can put them inside the Hamiltonian and assume that they are gone. This goes against Hamiltonian formalism, or actually every time that you do derivative, if you want to do a derivative of df dx at x equal 2, you cannot plug the x equal 2 first and then do the derivative. Of course, this doesn't do justice to this whole work, because this is much more complicated than this. And elimination of the nodes were something very popular back then in the 60s to do, so they did it as well. But now let's relax this. If we ignore this and do include the fact that I have, and this had stopped working. Oh man. If we ignore this and do take into account the fact that that it's not conserved, then our equation that we saw before is fine, right? Remember this equation. Oh my goodness, this is really bad. This equation is fine because this is okay, because then I have something that is changing with time equal to something that is constant plus something that is changing with time. So we're fine in that respect. Okay, so what did we do? We just took everything and rederived it, including one more thing. Now, remember that I said that in the quadruple level of approximation, the angular momentum of the outer orbit is conserved. I have a symmetry for rotations. That means it's completely stuck. Okay, thank you. That means that there is some inherent problem with a quadruple level of approximation. So when we think about this, when is this really conserved? Well, it's only conserved in a very, very special case. Only if my outer orbit is circular and one of my inner orbits is a test particle. only then, if you think about this, the only thing that is conserved there is the z-axis, is the z component of the angular momentum. This is the only thing that will be conserved. But if we want to include eccentric outer orbits, as we know that there are many of these, we need to go to the second level of approximation, which is called the octupole. This had been done before us, and basically I think that everyone could have seen whatever we are seeing way, way, way before us, but somehow it was missed. And we found that rederiving everything, allowing the z components of the angular momentum of both the inner and outer orbits to change, we can tap now to larger parts of the parameter space. And the behavior of the system is far richer and exciting than was thought of before. And it means that one more thing, that if I have a star and a planet, it means that if I have a perturber, I may flip a planet, which is nice. That means that I can go from below 90 degrees and go to above 90 degrees. And of course, it went the other way here, but this is what I can do. This is, I can do it this way. I can do it that way. A little joke, little laughs, it's fine, thank you. Anyway, so here is an example. I have here the inclination, 1 minus e. This is for the eccentricity. We care about 1 minus e because we care about pericenter passage. That means that here is circular, here is eccentric. This is the z component of the angular momentum of the inner orbit and outer orbit to make the point, and this is time. And we can see, just like as I said, it oscillates from inclination and eccentricity oscillates. And here it started from below 90 degrees, above 90 degrees, below 90 degrees, above 90 degrees, and so on. And here we can see these very interesting eccentricity peaks that goes to very high eccentricity. It means that the planet spends a lot of time around the star. Just to push down this point, this is what happened if you do it with a nominal way. This is the blue behavior, and you can see that there is a qualitative difference between the two calculations. Another example, this example showed that the behavior is not very regular. You can see that it's hard to define, for example, regular timescale. The behavior should be chaotic. These are three-body systems. They should be chaotic, and they are. So I have a few questions, which I'll probably manage to do one of them. My question is, why the inclination should be high? And not only high, it should be actually larger than 40 degrees. And do we find that we have to be in high inclination for the eccentric quasi-Lidov mechanism? And what about the chaos? Where do we see the chaos? I will start by answering yes, no, and then I'll just shoot to it. So why high inclination? I'll explain this. This means that we do not require actually high inclination to trigger the eccentric quasi-Lidov mechanism. And chaos, yes, chaos is there. To explain the high inclination, I want to take us back to pendulum. Now, I'm using this to explain the quasi-Lidov, but basically, every time that I talked about resonances, we can go back to the pendulum and understand this. Thinking about the pendulum, if I start moving the pendulum like this with a small angle like that, I can plot this plot in the momentum and angle phase space. And then I can try to do all kind of different initial angles, like this one, for example, and get a slightly bigger eye, like this. So I call this an eye. And then another big angle, and I can even go bigger and have a completely different behavior. And if I'll plot all of these on the same plot, I'll get this behavior, and here again this is P and an angle, and I get two different types of behavior, what we call libration and what we call circularization, and some of you may know it as rotation. And the thing that separates the two behaviors is called the separatrix. And basically we can think about the very simple quasi-Lidov mechanism as a little bit complicated pendulum. If I start from an eccentricity of 0, I can have very similar kind of behaviors here. You can see here the libration, and over there we have the rotation. And these are very similar behavior to the regular pendulum. It's a little bit more complicated because unlike the regular pendulum, what we have in the quasi-Lidov mechanism is that, I'll just finish my sentence, is that the prefactors in the Hamiltonian are not constant. So it's more complicated. And then you find that the separatrix, if you start from eccentricity of 0, is exactly at 40 and 140. So this is why we have high inclinations. And I'll stop here. Thank you. You're so sweet. Caitlin asked a question. Thank you. Why do we no longer need high inclination? Because I said we don't need it. Well, the reason is because we went to the higher order of perturbation. We allowed the system to be eccentric, the outer orbit to be eccentric, and this is work led by my former student Goncier Lee, an excellent student. And what she showed is that if you remember those nice plots where I showed the libration and the circularization, if we have more parameters in the system, then we need to do a cross section because we basically want to look only on the projection, as she explains here, and the trajectory. And here we see the libration, and here we see a lot of the chaos, for example. But what it meant that we can now go from very low inclination to almost 180. And back and forth, and the only requirement is that we will start with eccentric inner orbit and eccentric outer orbit, and the systems are almost coplanar. So even if I'll start with 0.01 inclination difference between the inner and outer orbit, I can flip and get a very high eccentricity. Look how high it goes over there. Very high eccentricity peaks and re-trigger this behavior because we have high orders of resonances that can be seen here. So these are the regular Kozai resonances, and here are the high order resonances, and they are ruling the behavior. Thank you, Caitlin. Yeah.
How many orbits does a flip generally take?
Oh, that's a very good question. So the question is, how many orbits does a flip usually take? So I will answer. I'll have 3 parts to the answer. First answer, let me remind you that we're working in the secular approximation. That means that the average over the orbits has to be valid. And in other words, if I'm doing 1 or 2 orbits and I'm thinking that is fine, that it's actually not. So I have to make sure that whatever the planet or whatever object you want will go around its orbit many times to be comfortably using this type of approximation. Okay, so this is one, and then the question is when does the flip occur? And we have 2 different regimes. One regime is taking place in high inclination. So let me go to the high inclination movie. And here, for example, we have a movie that shows the high inclination starting with an eccentricity of approximately 0. And we can see the flip. So here we have a perturber far away somewhere here. And the flip, if you want to look at the flip, you can look at this pink arrow, and here is the flip happen now. And usually it takes about between 50 to 100. If you are in the very ordered, not a chaotic regime, then maybe you can get a more analytical expression, and there are people who did this. But very roughly, right now, I can tell you between 50 and 100 low quadruple oscillations to get a flip. However, if you look at the low inclination, in the low inclination regime, you can see that the behavior is completely different than what I showed you before. And the flip happens very quickly after about 5 quadruple level oscillations. And also the behavior is different because the precession of the different angles behave differently. So the question was, the beauty of the former quasi was that there was some very simple relation between eccentricity and inclination. They oscillated in a very nice fashion. And the question was, do I see a significant difference from this? Am I correct? So first of all, at least in the high inclination regime, everything is driven by the lowest order of resonance, which is the quadruple level, the old-fashioned quasi, if you like. And the high-level resonances, the high-orders resonances, sorry, the high harmonics, what they do is that they drive things to be more exciting, if you like. So you can see these oscillations here as well. See the oscillations from inclinations and eccentricity. It's not integrable anymore. So I cannot tell you what will be the maximum eccentricity here unless it's some special case of a test particle and so on. So that is the point. That means that it became much richer than going only up to this eccentricity as shown here in the blue. So the basic level is there, but you will not reach the same eccentricity, you will not reach the same behavior. The system is qualitatively different. And it's still pretty, at least in my mind.